Institute of Engineering and Technology.
Hello students, today we are going to discuss about a test which will help you to check whether given series is convergent or divergent using integration of the function. In this test, we are now going to discuss about convergence and divergence using functions integrability, and we'll use a concept like decreasing function, continuous function and a function which is integrable. So ultimately in this talk we are going to incorporate integration into the convergence of series. We have already discussed two fundamental series and their special cases, geometric series and p-series. Also we have gone through a detailed discussion of what do we mean by convergence of series and divergence of series. And we also considered our first test, which was actually nth term divergence test for the given series. So I hope all of you have gone through all those videos and all those discussions which we covered previously. Today we are moving forward towards our first test which will help you actually to check whether given series is convergent or divergent. So in that case, let us start our first part, that is infinite series, with help of integral test. So the first thing about integral test is how we can define it for any series. So the theorem is like this: for any series summation a n with n equal to 1 to infinity, if sequence a n is a sequence of positive terms and f of n is equal to a n, then this function must be continuous, must be decreasing, and it must be for the positive numbers, and so it is positive valued function for all n greater than or equal to capital N. This simply means that for initial values it may happen that function is or a series is behaving randomly, but after that capital N index a series will fall into a particular form. Our given series must be in a decreasing form, it must be continuous, and it must be with the positive numbers only. If all these three conditions are satisfied, we can define a function on these values of a n, which is given by f of n. And if these conditions are satisfied, we can go for its integration also. So if that particular part from capital N to infinity is considered into the calculation of integration, and if that integration is finite, for sure we can say that this series is convergent. Now how this is happening? Why integration is used in case of series? For that, let us consider its graphical representation. And for that, I am considering one particular series which we know is a p series with p equal to 2, so it is convergent. So I am taking summation 1 upon n square for n greater than or equal to 1. If you look carefully, the series is convergent series, but now I want to approach towards its convergence using integral test. So what I will do, I will define a function which is given by f of n equal to 1 upon n square. And so if I integrate that function from 1 to infinity, f of x dx is 1 upon x square dx. And we know the integration of 1 upon x square dx over 1 to infinity is a finite quantity. So ultimately our integration is finite for 1 upon x square. That simply means that area under that function is going to remain finite. And if area is finite, that means that curve is going to touch, or it is happening that it will move parallel to x-axis after certain level. And if that curve is going to move parallel to x-axis, or after certain stage it will merge to x-axis, we can say that all points on that functions are now lying on the x-axis. So that will fulfill our condition of convergence. So the whole idea of integral test is something like this. You take a function which is represented by all those points. So ultimately you are finding a curve which is passing through all those given points of the series. And then you are integrating it. So you are finding area under that curve. And if that area is finite, that means that curve will merge with x-axis after certain level. And that simply means that all points on that curve will go on to the x-axis. So this is how this integral test is very useful. It will help you to not only check whether it is convergent or not, but it gives you a totally new aspect of convergence with help of functions integration. Now let us check our P series for this integral test. At the time of discussion of P series, I already told you that we'll go for its proof later on. So now I am discussing the proof of P series, that for which value of P it is convergent, for which value of P it is divergent. It is now using integral test. Let us consider this P series 1 upon n raised to P with n equal to 1 to infinity, our standard P series. Now if you want to apply integral test on this, I need to assume f of n as 1 upon n raised to P. So f of x, which is nothing but 1 upon x raised to P, is going to be a positive function. It is going to be a continuous as well as it is decreasing by nature. So now I am dividing this value of P into three categories. First of all, I am taking P greater than 1. Now if I integrate 1 to infinity f of x dx, it will give me 1 to infinity 1 upon x raised to P dx. By taking simple rule of integration, it is x raised to minus P plus 1 upon minus P plus 1, x from 1 to infinity. And then later on I will apply the limits 1 to infinity, which will give me answer 0 minus 1 into the bracket. The reason over here is P greater than 1. So the power of A, which is 1 minus P, it will give you a number which is less than 1. So power of A is now from 0 to 1, and then if value of A is increasing, which is moving towards infinity, ultimately that whole number A raised to 1 minus P is reaching towards 0. So this is happening because P is greater than 1, and therefore ultimately it will result into 1 minus P in denominator, and so it gives you a finite quantity, which simply means that this integration is convergent, and so the series which is defined with help of this function 1 upon x raised to P must be convergent. Now let us consider another case. If P is less than or equal to 0, clearly by nth term derivative test we can say that this series is divergent. You may take any number. If you take P equal to 0, it is 1 upon n raised to 0, so it is 1. So it is a series with the constant value 1, so ultimately it will go for infinity. If you take any negative number, for example, for simplicity I am taking minus 1. So it will give you 1 upon n raised to minus 1, so that denominator's n will jump into numerator. So it will give you summation n equal to 1 to infinity n, and obviously it will go to infinity. More the number or the more the value of P, the fastest approach toward infinity will be seen. And this is the reason why for all P less than or equal to 0, this series is divergent. Now let us come to that particular part in between 0 to 1. What will happen if your value of P is in between 0 to 1? Again I am taking the same approach, I am taking limits, but now what will happen to the power of A? Now it is minus P plus 1 and P is in between 0 to 1. So ultimately that whole number 1 minus P is going to be a positive number. And that positive number with power of A tending to infinity will blast towards infinity. And so it will give you answer infinite. So if you take P from this range 0 to 1, obviously your answer is going towards infinity. And now let us check the last case. What will happen if P equal to 1? For P equal to 1, it is nothing but a harmonic series, and so it is divergent. So let me combine all these three cases. If your value of P is strictly greater than 1, then and then only it is going to be a convergent series. If value of P is less than or equal to 1, then for all different possibilities it is going to be a non-convergent, or in some case you can say divergent series. Now let us come to the limitations of this series. There are certain limitations of this series, in which case we can apply it, and what are the other limitations. The first limitation is the integral test is only and only about verifying whether the series is convergent or not. There is no relation with the infinite sum from this series. Like in case of P series, and if P greater than 1, then it gives you answer integration 1 upon 1 minus P. This simply means that your series is convergent. This 1 upon 1 minus, it doesn't give you any idea about infinite sum of the series summation 1 upon x raised to p. This simply means that we cannot find our infinite sum using integral test, which was actually possible in case of geometric series. So here we have only condition that it will give you idea about convergence and divergence, but it will not give you final answer of the summation of the terms into the series. Another limitation is your function must be decreasing, your function must be continuous, your function must be positive, and more on that, it must be integrable. Then and then only you can apply this test. Now let us consider one example. For example, if I want to take summation n e raised to minus n square with n equal to 1 to infinity, and I want to check what is happening to its convergence. To apply this integral test, I am assuming a function f of n which is given by n e raised to minus n square. Now I am taking integration from 1 to infinity f of x dx. So give me 1 to infinity x e raised to minus x square dx. Now I cannot integrate this directly. So for that reason I am assuming x square equal to u. And that gives me 2x dx equal to du. Finally, by taking values of integration, it will result into 1 upon 2e, and this simply means that my answer of integration is finite. And this finite answer of integration will lead towards the convergence of the integration. And so by integral test, we can say that the given series is convergent. And therefore, by integral test, now we can say it is convergent. Now if you look carefully, I have represented this thing graphically also. Now if you look at the graph of this function x e raised to minus x square, which was actually derived by f of n equal to n e raised to minus n square, it is denoted by that red graph on the xy plane. And then I have considered the points from this series by blue dots onto the curve, and then I have represented it by blue bars. If you look carefully, for the certain initial level, the series or the function, they are increasing, and so we cannot apply this integral test. But after certain level, you will observe that it is falling under the conditions of integral test. It is continuous, it is divergent, it is decreasing, and it is positive. So it may happen that for the initial or the finitely many values, your series is not obeying the rules of integral test, but after certain level they are falling into the conditions of integral test. So here if you look carefully, initially my values are moving into the upward direction, and then it will go into the highest point, and then it will start decreasing. Once it will approach towards highest or the biggest values of n, it will move towards x-axis, and slowly it will merge itself with x-axis. And this simply means that area under that curve is finite, and so the points on that curve, they are going to be on x-axis after certain level. This simply means that we can find addition of all these heights which are represented by blue bars, and that ensures you the convergence of series. So I hope all of you understand this first part, or a first practical test, or the first approach towards checking convergence of series mathematically using integration of the function. Later on we are going to discuss other test is like what do we mean by root test, what do we mean by ratio test, what are the alternating series, and what are the absolute convergence. Thank you.
LJ Institute of Engineering and Technology.